Okay, so we now have the equations of motion that we want to use. Let's do a couple of examples just so we can get a handle on how what those solving those equations of motion might be like, or maybe not even solving them, just kind of thinking a little bit more about the Coriolis force, thinking a little bit more about that rotating tank example that we saw, thinking a little bit more about what that implies. Okay, so hydrostatic balance, still our classic example of a dominant balance, but now we see, hey, look, we're actually imagining these to be in our tangent plane. We've got the Coriolis force. Where did the pressure gradient force go? Oh, well, it's in G now. So even though G, we might think of it as gravity, we're actually expressing this as both gravity and centrifugal force are included in G. So G is in the local vertical, which remember is the direction that mass in a string would hang. It involves both gravity and the centrifugal force. And then we got some friction term over here we had talked about. We got the material derivative over here. All right, and so we talked about the local vertical being not equal to the direction of gravity. It's also true in the tank, not equal to the direction of gravity. It's got this little bit of centrifugal force, and that is why this surface gets sloped, because you need a pressure gradient force that's pushing back to balance the centrifugal force and keep the fluid from sloshing out of the tank. We went through this bit of the equations of motion, and we settled on this being the simplest form, at least for an F-plane. And now we closed on the idea of Rossby numbers, which is basically asking how big the advection or the time rate of change term is compared to the Coriolis force. And I went over this part quickly, but basically in the typical ocean and atmosphere cases, we expect both the advective and the temporal Rossby numbers to be small, because we expect the motion to be on very large scales, or the velocities to be quite small compared to the velocity of the rotation of the Earth, or very long time scales, much longer than the period of a day or a factor of a day, proportional to a day. We'll get a little bit more careful about what we mean by day in particular in a moment, but both of these numbers we expect to be small often. Okay, the Taylor-Proudman theorem, this is after two early 20th century scientists, Taylor and Proudman, who were interested in how rotating tanks and rotation and the rotating fluids in the atmosphere and ocean worked. And what this tells you about is what typical flows result from the Coriolis force when there are no other forces important. And so we're going to consider the small Rossby limit where rotation is dominant. Okay. In the limit of small Rossby, we just drop that material derivative term, boop, boop, gone. And this is what the force balance looks like. Now we could, this is inside of a gradient, this is inside of a gradient. If the density was constant, we could assemble these together, just like this, pull the density inside, bring the pressure, so we have pressure plus the gravity and centrifugal force, all here together, hiding inside of here, and neglecting the frictional forces, we drop the F prime, bingo, this is what we got. Okay. This is a complicated equation. What could we do? Well, we could take the curl of both sides. Why would we do that? Well, because this is all a gradient on this side. So if I take the curl of it, it just goes away. There is the curl of gradient of anything. It doesn't matter what the pressure field looks like. Or density field has to be constant, but it doesn't matter what the gravity or centrifugal forces, what directions are going, anything. It doesn't matter whether we're talking about the tank or the planet or anything. This is all inside of gradient. Take the curl of that, it's gone. Bingo. So the curl of this side, curl of 2 omega cross B, is 0. All right, that's weird. What kind of motion is allowed by this limit? And remember, we're already in small Rossby, so we don't expect the advection so we expect this to be appropriate on large length scales, long time scales, where this term is at least negligibly small. You might want to go through this again and say, oh, well, we dropped friction and we assumed constant density, so maybe an approximation would have been better here. But if we take those exact, this is the exact result. Let's expand this out and see what this actually tells us. Well, the omega cross omega is a triple product and so you might remember your triple product identities from multivariate calculus. If you don't, this is what you get. You basically want to distribute these derivatives out. And so you get one term that goes like v dot grad, looks like a material derivative, except it's on the 2 omega. Then you get a 2 omega dot grad acting on v. Then you get a 2 omega times the divergence of v, and then you get a v into 2 omega times the v times the divergence of 2 omega. Well, 2 omega is constant everywhere in space, so its divergence is 0, and so is its gradient. This term and this term are gone. If we're incompressible, this one is gone. So then the only one that's left is this 2 omega dot grad v. 2 omega dot grad is something in the direction of 2 omega, that is in the direction of the rotation axis, looking at the components of v, u and v, two different directions. 2 omega dot v says, in the direction of the rotation axis, the velocities do not change. The flow is stiffened. You don't tilt over. If you were going to tilt over, that would mean that the velocity higher up and lower down in that direction of the rotation axis would be different. This is saying that doesn't happen in this extreme limit. So now let's go back to our movie. Remember what happened in the rotating tank case? It spreads out like curtains of flow. So the velocity at the top of the tank and the velocity at the bottom of the tank, to decent approximation, are the same. We don't see big shear that is different velocity at the top, different velocity at the bottom. Instead, we see curtain-like or Taylor columnar motion, or Proudmann pillars, if you want. All of these kind of vertical structures that are unchanged in this limit of flow. All of this water has roughly the same density, so that's not that. But what's this little leftover bit? That's definitely a shearing motion where the surface and the bottom are going in different directions. That wasn't allowed in our low Rossby number ignore friction limit. What's that about? Well, let's come back to that in a second. Here's the Taylor columns like this. They're moving around, doing their thing. The ink is just saturating those columns and making those curtains as it goes around. And that's exactly the kind of motion that this equation describes. Two-dimensional motion where the velocity at the top and the velocity at the bottom are the same. You could draw little columns like this around the Earth, and you would expect those little columns to move. Except that's a little bit funny for the same reason why we did the tangent plane approximation before. It's actually the local vertical that is maybe, and the tangent plane that's maybe the more useful version of Taylor columns here. So we might expect within a local approximation that the motion would be stiffened in the direction of the local vertical based on the projection of the Coriolis, the F vector into the local vertical, more than into the direction of the planetary rotation axis. Why is that? Well, because actually we have neglected the variations in density, and it's the variations in density that make the local stratification align with the local vertical. So there are extra forces in that direction that we don't want to worry about. But if you're talking about rotating around the local vertical, if the stratification was relatively flat, you wouldn't have any density effects as you're just going around and around in a layer in that direction. If we go to Jupiter, on the other hand, then you actually can see some of these things, these banded stripes and these column. And then if you have seen these polar vortices, which are so amazing and cool from the new satellite or the new, what are they called? The new probe that went by over the polar orbit of Jupiter. You see little eddies here, and then you can imagine that there might be tall columns linking these bands of Jupiter, all aligned in the rotation axis with a north pole somewhere around here. Taylor-Proudman theorem doesn't apply generally. It's not a lot like the ocean. What are the exceptions? Well, friction. We're going to talk about that next. That's the Ekman layer problem. Time dependence. So those wobbles that we saw were one example. We're going to talk about the equations that lead to that in a second. And then density variations. So that's going to result in something called geostrophic shear, which we're going to, or thermal wind shear, which we're going to spend a lot of time talking about. Okay, so in the F plane, where we have moved into that plane that's perpendicular to the rotation axis that's perpendicular to the stratification, then we have this F dot gradient of U. So it means that in the local vertical direction, we don't see any velocity in the U and V and W in the direction of the local F. What could break such a symmetry? Well, any of the other terms in the equation. So we could consider friction and turbulence. That would be the Ekman layer. Or we could consider, if we zoom back in and think about the wobbling of those curtains, a little bit of time dependence. Here's the time dependent part. Let's see if we can solve these equations if we throw away the advection term, the V dot grad V from here, but not the ddt. Okay, well, the equation we get, we do the same. We could combine these two, the centrifugal and the Coriolis force over here, centrifugal and gravity over here, put in gradient and neglect friction. And then we can take the curl and we can think how that goes. But let's just look at a simpler case where we just assume that all the forces on the right-hand side are all zero. So now we have just the ddt and the 2 omega cross V equals 0. Time dependence and Coriolis force. Well, if you plug this out with the two components, the U component goes with the term over here that's got the V component, and the V component has got a term over here that goes with the U component because of the cross product. So bingo, U du dt minus 2 omega V dv dt plus 2 omega U. Okay, well, hey, look, there's U, V, V. Can we combine these two equations into one equation? Yeah, of course we can. We can take a time derivative of either one of these and then substitute the answer. So time derivative of this would give us a second time derivative of U, first time derivative of V, because 2 omega doesn't vary in time, but we could take that and substitute into this equation. So and we do that, we actually would get a second derivative in time and another term that depends on 2 omegas. And in fact, it's solved, as you might expect with a second derivative in time equation. It's solved by cosines and sines that vary in time. Bing, 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 like this. If you doubt me, you can plug this in up here. You get the cosine part, take the time derivative, and you get a sine. And that gets canceled by the sine from this term and this term. You do it the other way around. The sine from here gives you a cosine that gets canceled, etc. Okay. So what is this telling you? This is telling you that there is oscillations in the U and V velocities going around and around, wobble, 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 with what period? A period of 1 over 2 omega, or in the angular period. But since omega is 2 pi per day, that's saying twice per day you do this wobble. Or we could do it in terms of F. We get the same thing. So now we have F. So F is 2 times the sine of latitude. So in the tangent plane, there's actually a sine of latitude connection. So the time scale, 2 pi over F, 2 pi over 2 omega sine of latitude, blah, 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 equals a day divided by twice the sine of latitude. So this inertial oscillation, which is what we call these things where the Coriolis force balances the time rate of change term, has a time scale of a day divided by twice the sine of the latitude. This is the same thing, the same kind of motion that drives a Foucault pendulum. And Foucault, even though he got the pendulum named after him, if you go and read his original paper, he says there's a correction factor of the sine of the latitude, which I don't have time to explain here. Yeah, it's not trivial. It's a pretty complicated thing to explain. We've been talking that through, and we knew what the answer was going to be at the end. But this object right here is sometimes called, without the two, is called the pendulum day. So this motion goes oscillates twice per pendulum day, twice, which works out to be twice per day at the pole, when sine of latitude is equal to 1, and equal to once per day at 30 north or 30 south, where sine of latitude is equal to a half. It doesn't happen at the equator because the vertical axis, the vertical rotation axis, is perpendicular at the equator to the planetary rotation axis. So this 2 omega dot z goes to 0. All right. What does this look like? Well, if you look at observations, there are these sort of loop-de-loop patterns. I'm doing it backwards, going zoop, 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 zoop. That's what inertial oscillations look like. This is a buoy that was caught in an inertial oscillation, and it's kind of a loopy trajectory. There's a mean flow imposed, but it's the looping part that is the inertial oscillation. And you loop in this direction, in this hemisphere, and in this direction, in this hemisphere. And if you're going around and around, the Coriolis force is always pushing you towards the center of that inertial oscillation circle that you're going in. And Wunsch actually shows these nice power spectra, which we talked about a little while ago. And you see that there's a whole lot of energy hanging around, 47%, 57%, 18% hanging around at that inertial peak. These inertial oscillations are everywhere. There is a MATLAB program, which you should go and mess around with yourself on the webpage. Here's where the download is. This is a fun thing to play with. It shows you the point of view in both the rotating frame and the inertial frame. It allows you to turn on and turn off the cancellation of the Coriolis, of the centrifugal force by the pressure gradient force. It allows you to think about things like, should the trajectory be a straight line in the inertial oscillation? In the inertial frame, should it be a straight line in the inertial frame if I turn off the centrifugal force? Those kind of things come through. I encourage you to go play with this. All right, so we have a new main balance, or a couple of new main balances to throw into our review of balances. Now we have the inertial oscillation, which is a balance between the time tendency term and the Coriolis term. And this is what it takes to get there. You need small advection. You need rotation and time change. Small advection means this term is small. Rotation and time change is small. Friction and density are small. All this stuff is small. And that's these values of these parameters. These are the key parameters that are controlling it. Ekman small, Rossby advective small, Rossby temporal order 1. Hydrostatic balance, this one, occurs when the aspect ratio of the motion is small. Taylor-Proudman actually involves these three terms, which this is now a funny thing where I expanded out whether this gradient was, whether the density varied or not, and gave it as a new term. If the density varies, then you break this balance. If there's friction, you break it. If there's either of the terms of the material derivative, you break this balance. So this sort of applies when it's rapidly rotating, friction and density variations are neglected, and the rotation axis direction is the only direction that's constrained by this kind of motion. So you can think about what it means in terms of the Rossby and Ekman numbers. Sorry, Ekman numbers like the Rossby number, but for friction. And then the next time we're going to talk about the Ekman layer, which is the balance between the correlated force and friction. And that's when the Ekman number is order 1. Rossby numbers are small. All right, thanks a lot. See you guys on Thursday, which is our next class.